All right. Hello, I am Sarah Glatter, and this is my ECE 591 neural network presentation. My project is about low-footprint multimodal neural networks. Specifically, I will be looking into dual modality image and audio convolutional neural networks and compare them to single modality CNNs. Here is an overview of my project presentation. First, I will discuss the introduction to the project, the inspiration and the reasoning behind this work. Then I will talk about some related works in this field. I will discuss the creation of the dataset used for this project, as well as the methodology of the experiments. Lastly, I will discuss the results of my dual modality NN project and the conclusion and future works. First, the introduction section. The main inspiration behind my project is in using multimodality NNs for Internet of Things applications. We spoke very briefly about IoT applications and how they operate. Simply put, you can have a type of device that operates singularly collecting data or sampling or taking measurements, a multitude of different applications. The IoT device uses edge computing to do computational work on the actual device before sending it to the cloud or to the data center. Some of the limitations of IoT devices are such. They can have only a limited storage capabilities, meaning that the size of the application that needs to be used for the device should be small. IoT devices can also have limited energy. For example, they could be running on renewable energy sources or be in a place without reliable electricity access. Also, time can be a significant constraint for some of these applications. This is because they can be real-time applications that need to be calculated and uploaded as quickly as possible. My motivation for making a dual modality neural network is to create an NN that can run on the IoT device itself and collect the results, and then send these results to the cloud instead of having to send them to the cloud first and then do the calculations. The other reason behind my choosing this specific project is that my master's thesis research is based on dual modalities and specifically storage and compression of dual modalities. It was a good choice for me to grow more accustomed to image and audio management and manipulation. The next session is discussing the two areas of related research in the field of dual modality neural networks. Audiovisual zero-shot classification. One of the related works that I reviewed, I also did for my literature review. This is the audiovisual zero-shot classification paper. This paper presents a multimodal approach for zero-shot learning classification retrieval of videos. In the past, zero-shot learning has been used strictly for images or visual modality. And this paper aimed to prove that using a multimodal is shown to improve the performance of zero-shot classification. It also created a way to determine which modality is the dominant one and the one better at classifying a video. The similarity of this paper and my own project is in the dual image and audio modalities. The second paper is titled A Look and Listen Multimodality Late Fusion Approach to Scene Classification for Autonomous Machines. This paper's abstract states that the novelty of this study consists in a multimodality approach to scene classification, where image and audio complement each other in a process of deep late fusion. The inspiration for dual running neural networks, which then concatenate, came from this project. However, there are many differences between this project and my own. Namely, the neural network's design is different. Also, the application of the neural networks is separate, with this paper being scene detection and my project being animal classification. Now on to the data set section. For my project, I actually collected my own data set. Doing this is time consuming and caused some issues with my neural network in some areas. However, I will be using this data set for my master's research project, so I started off anyways. I started by selecting 10 classes of animals and collecting 16 videos for each animal, a total of 160 videos. From there, I sampled the videos as such. I started with the raw video of the animal. I decided to sample the audio into chunks that were n seconds long, where n was 4 seconds. I then took a frame of the video at n divided by 2 seconds as the image. The image from the video was then pre-processed and scaled into 224 by 224 pixels, which is a very common input into CNN image detection models. Then I transformed this into a NumPy array, where 224 is the size of the image, and 3 is the red, green, blue color channels. In the future, I will also add more pre-processing steps here. For example, scaling the RGB to 0 to 1 values instead of 0 to 255 values. I will try mean image preprocessing and other preprocessing averaging algorithms. The audio was taken from its raw MP3 form and transferred into a spectrogram measuring 224 by 224. It also has RGB channels, and it was also transformed into a NumPy array similar to the image. The text or classification was taken from the video title, and it's created into a NumPy array with zeros and ones being a 10 scale NumPy array for the 10 classes. After I collected all of the NumPy arrays from video, I stored the image data x1 and the audio data as x2 and the classification data y into test, train, and validation sets. I stored 8 videos into the training category and 4 into both the testing and validation sets. Ideally, this split would be 50, 25, 25%, but due to the differing lengths of the video, this was not always the case. This way of separating the videos also brought some errors. For example, if one of the videos of the dog was a Burmese mountain dog, a large furry dog that howls, and this was in the training set, but another video of a dog was a Chihuahua, a small dog that yips, and this was in the testing set, it would cause some errors, which it did. Through this project, I discovered some of the errors of my dataset. I had too broad of a dataset. Perhaps in the future, if I choose a distinct breed of animals for each classification and then chose one type of animal for the entire dataset. For instance, birds, and then my classes could be different breeds of birds. I also did not do any data cleaning, meaning that I did not check the images and audio to see if I had any corrupt or contradicting data. In the future, like I mentioned, I will retest my project with 2 new data sets. One would be a continuation of my animal data set with the different breeds of birds. However, I would pick one larger category of animal for the main group, and then the classes could be different breeds of that animal. For example, choosing 10 different breeds of birds to classify may cause less errors than having 10 different animals. I would also like to try a binary classification with an application that would easily used on IoT devices. For example, doing classification of detection of forest fires compared to normal forests may be a good idea, especially since the audio application could prove to be a good added adaptation to this already popular project. Now for the creation and methodology of my dual mobile network. My next slide is about the design of my multimodal neural network. This design is inspired by a paper written by Jordan Bird. I took the video data and created a dual running neural network that runs the image through a mobile CNN and runs the audio through another mobile CNN. Then I concatenated the 2 models before their individual output layers and added 2 dense layers with ReLU as their activation function, and then a classification softmax output layer. Here's a quick example of the code where you can see Yep, here's a quick example of the code where you can see I created the image model and I labeled all of the layers. I created the sound or audio model, labeled all of the layers. I then concatenated the layers, and then I created the dense layers, and finally the combined model. And after all of this, I trained the models. It is important to cover that I also created, trained, and tested 3 separate neural networks, one of which being, of course, the dual model I just covered. The first is just a MobileNet image model, which has just the image as inputs and the classification as outputs. The second is the one I just discussed, my dual MobileNet model or MobileNet dual model, which has the image and audio as the inputs and the classification as the output. The last model is the ResNet 152 version 2 model, which is the latest recent Keras deep learning CNN model. I also adjusted the last few layers of both this and the MobileNet image model so that they could have a classification of 10 images. All were trained with the same inputs. The only difference between these models was the 2 image models only had the image inputs, while the dual model had image and audio inputs. Also, it's important to note that I did not use the pre-trained weights for the ResNet 152 version 2. In the future, I probably would change that fact. Now on to the results section. As I just mentioned, I also trained 2 CNN models to test just the image data. I chose MobileNet and ResNet. MobileNet is a lower size and accurate CNN, where ResNet 152 version 2 is one of the more accurate CNNs available. However, it does have a very large size. The first results I will show you are the size outputs. For the size, by largest by far is the ResNet model, and the mobile image and dual are quite small. The first is the parameters, meaning how many trainable and non-trainable parameters the model has. As you can see, the ResNet dwarfs even the dual MobileNet, has 6 times the amount, and almost 12 or 13 times the amount for the MobileNet. The second is the amount of layers, how many layers the model has. Again, the ResNet is by far quite a bit larger. And parameters and layers are one of the best ways to measure the size of CNN models. Another way is to actually take the formula of the outputs of each of the layers. However, due to the size and the amount of layers, this would, even with doing by hand, would cause a lot of accuracies, and I could not find an accurate function or an accurate formula to do it by code. The last one I measured using a Linux bash command, the size of the saved models. I only saved the best model in each situation with the training. I'll show you how I did that later. As you can see, the ResNet model itself is 702 megabytes. And so this would dwarf any other components on an IoT device, just the size alone. And thus, the argument that I am trying to make for my project is that even if the ResNet has better accuracy in the future, having such a large model will take up storage for potential other data sets and other processing components. The next results are the time results, and the time it takes to calculate all of the test inputs, and then also the time it takes per image. Here you can see the MobileNet image takes 1.4 milliseconds per image. The MobileNet dual model takes 2.16 milliseconds per image, and the ResNet takes 5 milliseconds per image. This is a kind of estimate of how often it would take per image. I did, when I was running it, run all of the inputs at once. So that was all 1.2K results at once. Um, and so these are not exactly the time results that you would expect to see on the IoT device, because you would have to do the sampling from the video, which was already done pre, and that is more of a future works situation. Now, for the accuracy results, it is important to note that these results are very, very low. And they're also with the first hyperparameters I tried. I tried to keep the parameters pretty similar. Each of them used the Keras atom as the optimizer. The learning rate was 1 to the -7, 1e to the -7. Um, the batch size for the mobile net and the ResNet was 32. The batch size for the dual mobile net was 16, and this was due to some memory loss, running out of memory. And you can see for the training, the MobileNet had the best training accuracy, but the least best validation and testing. And same with the dual. Surprisingly, the dual's testing is very similar to the ResNet's testing. Now, these poor percentages are really honestly due to the data set and also lack of training. These were just, like I mentioned, the first hyperparameters. I did test other hyperparameters. However, it's hard to make sure that they all follow similar training to each other, and the accuracy did not change very much. You can see that the data sets really did make a difference, judging by the massive gap between the training validation and the training and testing, whereas the validation and testing did not have as big of a gap. Here is the training accuracy graphs of the all of the models. You can see it does go up, which makes me believe that I should probably have ran a higher epoch threshold. My epoch threshold was only 100. Here is the validation accuracy. Similar to the training. These do end up steadying out though. In conclusion, this project was a good start in the direction I want to take. There's definitely going to be some future work and future research that I will be doing here, specifically with the different data sets, and then also with finalizing how I train my models. Yeah. I want to thank all my classmates and also Professor Yifeng for this class that I had.